Hello, my name is Babak Rezapur and this is the lecture on large-scale hydropower for Renewable Energy Technology course. You've previously seen a lecture series 1 on micro and small hydropower by Dr. Brijesh, and today we are going to focus on large-scale hydropower. This lecture is divided into 4 series. On series 1, we start with an overview of hydropower in Sweden, and then we move to system components and different system layouts. Then we will continue with the turbine as the major component in hydropower, different type of turbines, and the selection criteria. On lecture series 3, we will focus on the performance characteristics. So we will move to the system characteristics of a large-scale hydropower. And we will continue and the last series with the economic of hydropower and social and economic aspects of hydropower. But what's the definition of a large-scale hydropower? In fact, there is no accurate definition regarding the size of hydropowers. It really depends on the countries, and various countries defines large scale and small scales differently. For example, in China, it's more than 50 megawatts, or in Sweden, if it's more than 1.5 megawatt, then it's defined as a larger scale. This is mainly because of the different legislations and licensing procedures in different countries, and in order to make eligible different schemes of hydropower plants under the different supporting programs. What is important to keep in mind is that there is in fact no direct link between the scale and the size of hydropower plants and their environmental and social aspects. For example, a large-scale 1,000 megawatt power plant in a remote river basin might have fewer impacts in comparison with a 200 megawatts power plant in another river basin. What is typically accepted is listed here on this slide, as you can see here. So for a larger scale, we can call it more than 100 megawatts power plant, which is categorized as the larger scale hydropower plants. Now we would look to the status of hydropower in Sweden, and we want to highlight a few major aspects of large-scale hydropower plants by reviewing the status of hydropower in Sweden. So if you look to here, on the chart here, you can see the precipitation per year, and then this is it can show that on west coast or the west region of the country, there is more precipitation comparing to the east side or the southern parts of Sweden. And on your right side, you can see the different elevations in the country. So it's more mountainous areas in the north, and you can see the rivers. The different hydropower plants are marked by these lines here. The red and yellow colors indicates the larger, so the red ones are more than 100 megawatt or 200 megawatts power plants, and the yellow ones are 100 megawatts. So if you look, it's more dense hydropower plants in the northern part of the country comparing to the southern part. This graph here shows the natural runoff in the river in the cubic meter per second in various months during a normal year. So in northern part, you can see that the runoff is quite higher during the summertime, mainly due to the melting of snow, which is stored on mountainous areas. And when we move to the southern parts, because of the weather effect, then the runoff becomes more uniform all along the year. And this is one of the main aspects of large-scale hydropowers. They could be used in order to uniform the runoff and store this runoff to be used in the other periods of the year. So the large-scale hydropower plant could be used as a storage, as some sort of energy storage. The graph on your right shows the unregulated production. So this is on the y-axis it's the gigawatt hour per week production. And then you can see the different months of the year. So if it's an unregulated production, then you can see that in June, July, when the more flow comes, then the production goes higher. But in fact, by implementing the larger scale power plants, which include dams building and storage, water storage, then the production could be regulated more uniform all along the year. On your left side, you can see more or less the same graph, which shows the gigawatt hour production per week. So on the bottom line here, as you can see, the hydropower production by the runoff energy. So it's more or less a function of the available flow all along the year. And this darker blue here shows the hydropower with storage energy. And in fact, this is the impact of making storage reservoirs through dam building or through pontage building along the rivers. And of course, Sweden is much dependent on electricity for during the winter time. So you could see here that the extra needed energy comes on top by thermal power during the winter times. This picture here shows an overview of the energy system in Sweden. You've seen this picture probably before or a similar picture, so I'm not going to go to much of the details here. What is important here for us is that if we look to the hydropower production in comparison, for example, with nuclear power or the crude oil and gas production, I have to say here that the oil and gas usage in Sweden is more or less exclusively for the transport sector. So here, and if you look to the total final energy used by sectors, so this you could see that the oil dominates the transport sectors. In the residential and service, the electricity is more or less half of the electricity which is used there, and mainly it comes from hydropower and partly from nuclear power in Sweden. This graph here shows the trends of the watt-hour or terawatt-hour production along the different years in Sweden along the past decades. So here, if we look to the 2012, hydropower counts for more or less 48% of electricity production, and nuclear power was around 38%. And if we look to the wind, then wind power accounted for around 40% of the total electricity production in Sweden. So now we have these aspects of this hydropower in Sweden. Two major things that I would like to highlight is one is the building storage through building dams, which enables Sweden to decouple the electricity production from the run of the river. So river flows could be stored and be used for electricity production for other periods or other months during the year. The second aspect is the connection to the grid, electricity grid. In fact, most of the, or I can say all of the larger scale hydropower plants, they are connected to national grids, and national grids are connected maybe to some other national grids. For example, in Sweden, we have a Nordic pool for the electricity the transmission, production and selling of the electricity, which enables connection of the Nordic countries all together. So in fact, being able to be connected to this network enables production of the electricity once it is needed and making it a regulated production. Now we take a look to the system components. So this is a very simple schematics of a hydropower, a large scale hydropower system, which consists of dam, intake and penstock part, the turbine and generator part, and the outflow or terrace. So if we look to the dam, there are different structures for building a dam, and the dam is connected to some sort of a tunnel or pipelines that enables transportation of water toward the turbine house. Along the way, there are different components. So it could be a tunnel, a sand trap, for example, trash rack in order to stop large debris in water. And then also we have the surge shaft in order to eliminate the pressure rise into this transport system, the penstock, and then of course the turbine itself. We will take a closer look to the turbine on the next series of the lecture. So this is an artistic illustration of a power plant. So here again, I would like to start from the intake. So these are the trash racks. This is called the reservoir. This is the dam body itself. Water transports through the penstock toward the turbine. And the turbine is in fact coupled to the generator, which generates electricity. And water released here through the draft tube into the tail race of the system. And of course, there are many auxiliary systems around this turbine collection, such as transformer rooms, control rooms, flow regulation rooms, and so on and so on. The placement of the power station itself, it could have different installations. For example, here the power hose is within the dam body, as you could see here. So this is the full reservoir level, and then this is the power hose itself. And then this one, the powerhouse is located at the toe of the dam. The powerhouse could also be located somewhere else along the in the area along the system. So here, for example, you can see on this section from a project, this is a lake, and then water could transport it through the tunnel, through some under the mountainous areas toward the powerhouse, which is located in some other locations. This is a slide you've seen previously by Dr. Brijesh, and it shows the classification based on head. And in fact, available head is the most important criteria in making a turbine selection and making a hydropower plant scheme. So we have a small head, or we have a high head schemes, and in between comes the medium head schemes of the power plant. We start with a low head. So here you can see a bulb turbine, which is located under the powerhouse. So the difference between the elevation of the intake and outlet is not considerable. Normally we call it a low head when it's below 10 meter or 15 meter maximum. And this one shows you a plan and topographical contours of an area. So each line here has the same elevation level. So you could see that this is the main river which goes in this direction, and then there is a diversion canal which in fact diverts the water through this channel and then brings it toward the power station. And from the power station, then it is released into the tail race. This shows the profile of the same system. So this shows the conversion channel. And then here, water comes by gravity through this channel toward the pump station. Toward the turbine. So the second type is the plant fed by a pressure tunnel. Again, you could see the contour levels here, the river that goes around here. Normally, a small dam or barrier is created here to make available a very short amount of storage for water, and then water is transported here through the tunnel toward the powerhouse, which is located here. If you look to the plan here, you could see that water goes under the mountain or under the high elevated area in a pressurized tunnel. And then comes finally the plants with storage. These plants actually they are built based on building a dam and then making a storage available for water, and water will be released through the intake toward the power station. So here on this one, this shows a concrete dam here. So the material of the dam is concrete. You could see the water intake and water flows toward the pump station. This is another scheme here. This is another type of dam here. The power house is located beneath the dam on the downstream side. So this availability of the area, the topographic of the area, and the site specification lead to the classification by facility type. So mainly there are two different schemes: runoff river or the storage facilities. If we look to a runoff river, then there is no storage at all, or very limited storage for water in order to be sent to the power station. They could, for runoff rivers, could have two different schemes. They are either based on a very large flow and very low head, such as a large river here you could see on the right side, or they are based on a very relatively small amount of flow but high head. So you could see, for example, on this one, there is a channel here which diverts water toward this point to the 4-bay tank, and then water is released toward the pump station here. I took as an example here a project which is between the Switzerland and Australian border. So in fact, water is diverged from the river, and then it is transported invisibly beneath the mountainous area toward the powerhouse here. This scheme is around 90 megawatt. The cost of the project is around 400 million euros. This is going to be commissioned within 3 years from now on, in 2018. This shows, in fact, the intake toward the tunnel. So you could see the environmental, the visual impact is minimized. This is a very small, we can call it a dam or barrier here, in order to have enough water level here to divert water toward the tunnel. So nothing more could be seen on the river, not very specific visual impact on environment. So this shows the plan of the same area. So you could see the diversion tunnel here, and this is the dam that we talked about it previously. This photo shows the power station itself. This is the artistic illustration of the power station, but if we look to the section of this power plant, then we could see the pressurized tunnel which comes toward the power station here. So the turbines is in fact located at this area, which is cooled to the generator through the shaft or a rotor. And water is released again back to the river or the riverbed after electricity is produced on the power station here. Another example here, which is based on the large flow but very low head. This is an example from a power plant on Danube River. And the scale of the power plant is 287 megawatt. So it can be classified as a large scale hydropower plant. So here you could see the power station, which is located on the river. The flow comes in and goes out, and the turbines rotates within the power station here. The float gates are located on the right side of this picture. As you could see, they have a mechanism here to go up and down and control the level of water on the downstream, on the upstream of the power station. And of course, there should be some water lock here in order not to stop the boat traffic. So in fact, boats could travel toward downstream or upstream of the power station through the water lock mechanism. This shows a section of the gate flows that we saw previously on the previous slide. So you could see that this mechanism here is in order to make this head available. It's around 14-meter difference head between the downstream and upstream of the power station. This photo shows inside the power station, so you could see the scale of that building, which is built on the river itself. So you could see that this shows, in fact, the top of the generators on the mechanical hull. You could see these rails are for the cranes in order to make the maintenance and regular inspections of the turbines and generators. It's good to mention here that, for example, here on this map of Sweden, if we take a closer look to this area in the north area, so you could see that there are rivers that are coming toward the sea. And then there are different schemes here. You could see the different red dots, and each one is a power station, in fact. So it is called a cascading scheme. So just different power stations along one same river or river basin. So on this section here, you could see the elevation, the meters above the sea level, and the distance from the sea. And then you could see the available, or the existing, in fact, the existing power stations along the river. So we get back to this classification by facility type. And then the second type of the facility is the storage hydropower. This is a very simplified picture that shows a dam which is built a reservoir here, and then water is transported by penstock toward the powerhouse. So this is the concept of the of the storage hydropower, and this concept is used mainly for large-scale hydropower plants because it has some certain advantages, as we will discuss. This is an example from a power plant in Sweden. So you could see the dam which is built over the river. The power plant house itself is also located very closely to the dam. This is a log flume here, in fact, because this river is used to transport the cut trees. So here is a mechanism in order to transport the trees along the river here. This shows a plan of the same project. The power station is colored here with red, which is exactly along the dam itself. So this dam here, in fact, makes a water storage available for the power station and regulates the flow which passes through the dam into the river. The switch yard is an auxiliary equipment is also located on the bank of the river. So a section of the dam here which shows the different materials that are used for the construction of the dam itself and the water level on the upstream of the dam. Another picture here which shows the dam during the construction. So you could see the construction machinery on top of the dam, and then they are building, in fact, the core of the dam itself. We take a look to the section of the power plant. So water, you could see the intake, the trash racks are located here. These radial gates are in order to stop or even regulate flow based on the demand. The penstock, the turbine itself, which is cooped to the generator, and the draft tube. And this is a photo from the machine hall of the same power station. Another type of facility type is, in fact, a pump storage hydropower plant, but in fact it's a, let's say, a subcategory of the storage hydropower plant. The only difference is that the turbine is used also as a pump to pump up the water on the reverse directions toward the dam reservoir, and by this it makes it available option for the operator to produce energy or to use energy to pump water back again and make and store water to be released during the peak in the demand. So you could just go and see more information by yourself. Just you can look to the Dinoving power station. It's in UK, and you could see the scale is 1800 megawatts power plant. And also at the same time, it could be used as a pump station to pump water. It was planned initially to store excess power generated by a nuclear power plant in UK. And nowadays, it is used as a fast response to the very short-term changes in the power system. Because you know, you've learned previously that hydropower is very easy to regulate it. It's a fast responding energy production, so it could be in operation in less than few minutes. Another photo here which shows the inside of this hydropower plant. So I would like to wrap up this section, this layout of the system, by mentioning the Harsprånget power station, which is the largest hydropower plant in Sweden. So if you look to the here, it is a dam or a storage hydropower. So water is stored here on dam, and then it is released toward the power station, which is located at this section. And then water goes by these tailless tunnels beneath the mountainous areas and is released into the river on the downstream. So if we look to some specification, the head is almost 110 meter, and then the power production is around 1,000 megawatt of its installed capacity, in fact, not the production. So this photo here shows a section of the dam itself, the level of water, the different geological conditions of the dam and earth you could see here. There are 3 different units of turbines that are connected by penstocks to the reservoir here. They are located beneath the earth or beneath the mountainous area. And then this one shows how complicated it could be. So they have added a new power station to the existing scheme there, and then you could see that the tail race, the old tailless tunnel, the new tailless tunnels. There are many auxiliary tunnels. So in fact, if you look to the reality, if you look to what is built there, then it's a very complex network of tunnels. Many of them are for ventilation or for access tunnel, working tunnels. So it shows the complexity around building a dam or building a larger scale hydropower plant. This photo here shows you the inside of the turbine hull or the machine hull on the same project, and you could see the generators during the installation work. The turbine is located below on this housing, concrete housing. I would like to wrap up this session by showing some projects in order to get a sense about the scale of large-scale hydropower plants. Here you could see a photo that shows the divergence tunnels. It's located beneath a dam, so the dam will be constructed on top of these divergent tunnels later on. In fact, this is located in the border between Iran and Turkmenistan. This project was aimed to make these 2 nations closer and bringing more political stability. We will discuss about these aspects of larger scale projects later on in the other series that we have. You could see the construction machinery on the top. So the same project, this is the water intake. As we saw before, water goes inside and then goes under the dam toward the power plant station. This shows the reservoir. In fact, this is during construction. At this period of the year, the river, you could see it here, and then the river is diverged toward the other side of the dam during the construction phase. The very same location you could see during the filling period of the dam. So the dam is constructed, it is completed here, and then it is being filled with water. So you could see on the right side, it's the Iranian border or the Iranian land, and then this is the Turkmenistan on the other side. This shows the dam constructions during the construction phase. You could see the machineries that are in fact compacting building materials for the dam. And the dam is completed. You could see the completed dam here. This is the bottom outlet of the dam, and then this is the intake toward the power plant. So you could see the intake structure. This shows the upstream of the dam. The downstream is located on the other side, as you could see in this photo. So this is the spillway. When water level gets very high, more than the normal water level, then water is released through this spillway. And this is the structure on the downstream in order to dissipate the energy in water, and water will be released in the river. So you could see the Turkmenistan on right side and Iran on the left side in this project. And this is going to be the border, in fact, when the river is the border. So this photo again showing the reservoir itself. We will discuss about the environmental impacts of a large-scale hydropower plant in the last series of the lecture. But this photo shows how it looks like before filling a reservoir, and then you could see the same angle when the water is filled and reservoir is full. So you could see that those areas, large huge areas here, they are drowned in water, and water is filled in the reservoir. Thank you very much for this first series. We will now have a broad overlook to the large-scale hydropower systems, and then how they look like, the different components. And now it's time to move and then concentrate on the turbine as the major equipment in a hydropower plant. Thank you.